Hello, everyone. We are Group 33. I am Group Lead Tremayne Duffus, joined by my teammates Alejandro, Elisheva, Arley, and Kadeem. Our sponsor is Dr. Hank Zong, and our advising professor is Washim Ashgar, and our project is multi-class lung cancer classification. Lung cancer is within the top 3 most popular cancers by volume and is the deadliest cancer by volume. Despite this, lung cancer has a relatively low research and development rate. So our project is meant to address these issues by leveraging both classical and novel machine learning techniques to identify specific genetic biomarkers indicative of lung cancer. And our 2 main deliverables are a research paper that displays our findings for further peer review and research, and a web platform that allows non-technical users, such as physicians, to utilize the models employed within their research.
Approach. To ensure accurate lung cancer classification, we follow a structured approach. First, we pre-process and normalize high-throughput microRNA expression and methylation data, reducing batch effects and technical variability. Next, we apply VTFS and baseline models to select the most discriminative microRNAs. We then conduct a comparative biomarker analysis, integrating methylation markers to enhance classification robustness. These selected features are used in machine learning models, SVM, random forest, and SAINT to classify cancer stage and subtype. Finally, we evaluate model performance based on accuracy, sensitivity, and specificity, ensuring clinical reliability across diverse datasets. Project status. Our project has made significant progress in lung cancer classification. First, we reduced over 1,800 microRNAs to just 7 key biomarkers using 6 feature selection methods, improving interpretability and efficiency. In model development, SVM achieved 99% accuracy in diagnosis, 49% in subtype, and 52% in staging, performing best on stage 1 and showing strong recall for adenocarcinoma. Random forest struggled in staging and subtyping, while Saint Transformer excelled in biomarker identification but underperformed in classification. Our research paper is progressing with results analyzed, and an initial web app prototype is built for real-time classification. Moving forward, we'll validate SVM on external datasets, optimize deep learning models, finalize our research paper, and prepare the web app for clinical development. Feature selection methods. Feature selection is a crucial step in our project because it reduces dimensionality and removes noise, improving classification accuracy. By focusing on the most relevant microRNAs, we enhance lung cancer detection while making models more efficient. We use multiple selection methods, each with a unique approach. Full change identifies microRNAs with the most significant expression differences. Chi-squared measures statistical dependence between features and cancer labels. Lasso applies regularization to shrink less important features weights to 0. Information gain evaluates how much a feature reduces uncertainty. Recursive feature elimination iteratively removes the least important features. NCA, Neighborhood Component Analysis, selects features that best preserve class structure. VTFS, a deep learning-based method, uses transformers to learn optimal features. Comparing multiple methods ensures that we capture different patterns in the data, leading to more reliable biomarker selection and stronger classification performance. Overlap across feature selection methods. This slide visualizes our feature selection results. The bar graph shows the number of microRNAs selected by each method, highlighting their individual contributions. The Venn diagrams illustrate the overlap across methods, showing shared and unique biomarkers. By comparing multiple approaches, we ensure a more reliable selection, capturing the most critical microRNA for lung cancer classification while reducing redundancy and noise.
Now let's talk about classification methods. Why classifications? We want to predict patient diagnosis, cancer stage, and subtype based on microRNA expression. And also classification trains machine learning models to learn patterns from labeled data. We use 3 different methods: support vector machines, or SVMs, random forest, and SAINT. Why compare multiple models? Well, each classifier may perform better on certain tasks, and the model diversity is going to help evaluate generalization and performance trade-offs. Support vector machines, or SVMs, are powerful classifiers that find the best boundary, called hyperplane, between 2 classes. So the goal is to maximize the margin, which is the distance between this hyperplane and the closest data points, called support vectors. This helps the model generalize better and reduce overfitting. In our case, SVMs are used to classify lung cancer diagnosis, stage, and subtype. These are the updated SVM classifications results using only the selected features. Basically, we retrained the SVM using only selected features and fixed label leakage. The diagnosis was the one that performed best with 99% accuracy and 100% recall. And the subtype and stage struggled due to imbalanced classes. Now we're going to jump into a live demo of the diagnosed model. This is the full support vector machine pipeline for lung cancer diagnosis using selected microRNA features. First, we import all machine learning libraries and set up login. Then we load the top microRNAs from 6 feature selection methods for diagnosis. 56 were selected. And then we clean the data, remove label leakage, and extract X and Y. And then we proceed to split into trained test sets and standardized features. And finally, we train the model. So we can see we use the SVM hyperparameters for diagnosis, C.1, gamma 1, and kernel 1, and the accuracy was 99% for diagnosis. Then we proceed to evaluate the model and have some feature selection insights. So here we are going to be saving confusion, correlation, and covariant matrices. And lastly, we set the results for future use. Random forest is a powerful ensemble learning method that builds multiple decision trees on different parts of the data, and each tree makes a prediction. The final classification is decided by majority voting across all the trees. This approach reduces overfitting and improves accuracy, especially when working with high-dimensional microRNA data like ours. The idea is to apply this to the same diagnosis stage and subtype task as we did for the SVM. In this slide, we're showing preliminary random forest results, and these haven't been fully re-evaluated, so they likely suffer from the same label leakage and overfitting issues that we addressed previously in the SVM. Therefore, until we retrain random forests using the corrected pipeline, this number shouldn't be considered valid. So there's now going to be a live demo for this part.
This is a quick overview on one of the transformer methods used in the project. This is the VTFS architecture developed by researchers at Arizona State and Princeton. Essentially, it transforms the tabular features into tokens, and then constructs an embedding space using attention heads and a variational autoencoder, similar to how LLMs work. Then it searches this embedding space for optimal feature sets. So the important thing to note here is how our first run reduced the feature set from 1,881 genes to 988, so about half. This is the other transformer method used in the project, which is SAINT, developed by the researchers at University of Maryland. This works similarly to the last model, except for this incorporates intersample attention, so it focuses more on leveraging the relationships between genes. And then this screenshot shows the results of a downscaled version of the model on the miRNA dataset, where it was only able to achieve about a 50% accuracy when predicting the stage.
Hello everyone, my name is Arley Peter. So this slide introduces the graphical user interface, GUI, for a multi-class lung cancer classification system. Our goal was to create a simple, intuitive, and efficient interface for users like researchers and clinicians. We built the GUI using Next.js, React, Tailwind CSS, and TypeScript. Next.js ensures fast performance, React provides a modular structure, Tailwind CSS helps with a clean and responsive design, and TypeScript enhances reliability by preventing errors. We focused on a minimalistic, distraction-free design to make the interface easy for all users. The file upload section is a great example, clearly labeled with the drag-and-drop support and manual selection option. The neutral color scheme and intuitive icons keep the experience straightforward and accessible. Simplicity is crucial in healthcare applications. By reducing complexity, we ensure users can upload data, select models, classify results quickly and accurately without unnecessary steps. In short, our GUI is designed for speed, accessibility, and ease of use. By combining modern technologies with a minimalistic approach, we create a seamless experience for everyone. Thank you.
So here's a live demo of the app hosted locally. The front end is React JavaScript, and the back end is Fast API in Python. So we're going to upload a sample from the National Cancer Institute Genomic Data Commons. And we upload the text file, and then we're going to choose a model as the support vector machine. So what happened there was on the back end, it formatted and processed the data. Then it selected the features based on the highest performing feature set from the research. And then it made predictions on all three target variables. And then it outputs these predictions, and the user can choose to also download these results as a CSV. So here we can see that the model predicted the patient to be cancer positive with stage 1 adenocarcinoma.
Right, on the backend, we are using the Fast API to accept CSV or text files through the API upload endpoint, which is right here. And each file is saved locally in a directory with a unique ID for tracking. With that uploaded file, we pass it to our preprocessed data function, which then loads the input file into a pandas data frame. And with that data frame, we use our select features function to filter it to include only the top microRNA columns relevant for our classification task. All right, that reduced data frame is then fed to our predict sample function, which loads our pre-trained model and returns predictions for diagnosis, stage, and subtypes. The results are then stored in our in-memory results cache here, which I do believe is a dictionary. which enables quick retrieval and download from our API status / file ID and API /download / file ID endpoints.